This conference will now be recorded.
On hardware-software trade-offs in radars, software-defined radios, avionics, and controllers. There are some logistics before you get started. This is a one-way conversation, so if you have any questions, there's a chat window in the control panel on the right-hand side. Feel free to click on the chat box and a window will pop up where you can type in your questions. There are a few application engineers waiting, so and they can immediately answer your questions. Also, if you send your questions as and when you think about it, I can also try to incorporate it during the presentation. With this, I would like to get started. Today, the topic is hardware-software trade-offs in radar, software-defined radios, avionics, and controllers. Now, this is a fairly complex or a fairly involved topic because today, most of these decisions are made after the fact, after the Simulink algorithm has been developed or after some RTL code has been written or some software that has been downloaded off the internet and used. Only after that, the decision is to be made as to which computer do I use or which ECU do I use for the processing of the signals, either at the the signal cleaning or filtering, all at the sensor fusion level. In this case, we're offering something which allows you to be able to make those decisions way before you even start your signal processing algorithms. Now, we're going to start off with some background information on system architecture exploration, then move to system modeling, and then we're going to look at the specific requirements for radars and signal processing, show you some demonstrations, and then talk a little bit about Mirabilis design. The presentation is expected to take about 45 minutes, and you would have about 10 minutes for additional conversations and any discussions that might have been skipped during the time. So going into the background information, today, if you look at the approach, the focus is really on the correctness of the mathematics. So you might create a signal processing algorithm, you might look at the poles and zeros, look at the signal integrity, or you might assemble up a block diagram that shows all the different parts of your radar system. So for example, your antennas, your RF, your signal processing baseband, the display systems, any other elements that go about in your design really would be more on a requirements and in a model integration platform where you would plug in your code, plug in your test cases, things like that. But what is really missing with this approach is right up front knowing, what kind of a hardware should I be using? Should I use a Mercury board? Should I use a 64-bit, ARM processor, or use a 12-core Xeon processor? Should I use the DDR5 memory, or should I have two boards and then distribute the workload across the boards? So really no visibility into what will be my response time, what's the power consumption. That is where our approach diversifies. Is we add a systems engineering layer on top of the current activities. So we extend model-based systems engineering where we allow you to create a virtual prototype of your full system. So full system is anything from the point that you get, it starts off at the tracking, which probably is an antenna, going through the AFE, all the way to the other end, which is the the display. So all the electronics, all the software, create a virtual prototype of the whole thing. In this case, the algorithms that might be in your analog system or might be in your signal processing, we wouldn't put in all the details that you would put in say your Verilog or say in your Simulink model, but rather it'll be abstracted up to like how much time it's going to take on a certain processor or a certain hardware block or an FPGA, the amount of data access, so which is like going into the memory and getting data, and of course any sort of expression that can be utilized to say that the data coming in, we did this kind of a processing and we took it out. So abstracting out all the information, that way you don't have to actually put in all the algorithms here and then again put it in Simulink, but rather keep your Simulink model, but here you spend the time providing enough information so you can make the decisions about your hardware and software. Now, Let's look at the traditional approach, and let's look at how the approach is on the proposed side. The traditional approach is, in this case, we got a sigma delta A to D. So that's your digital and that's your analog. So you can see the digital system has its FIR filters, a moving average, and a quantizer. And you can see that's your discrete results. This one here is a zero hole with integrators and periodic samplers. And you can see what the analog signal looks like. So here you can see how they match up or they don't match up because of some delays. And you can see the correctness of the algorithm. Now, the proposed approach, in this case, we're looking at a high frequency radio, involves the antenna, a switch with two transceivers from analog devices, a Zinc 7000 FPGA connected to an Ethernet interface. So within the transceiver, we model the power levels, FIRs, but all of these are modeled as a combination of delays and data sizes and some sort of simple expression. But you can see we have the I's and Q's. The main goal here we're trying to do is look at what is my end-to-end latency, which is from the time it goes from the antenna to the Ethernet interface. Look at what the power consumption is. The red line shows you what my average power is over time, while the blue lines show you what the spikes are. Here, you can actually see the activity associated with the memories, DSPs, the pre-processing, FIFOs, showing when all these different devices were active. Plus, you can look at just the DSP alone, or you can look at the statistics, like for example, on a particular buffer, what was the buffer usage and things like that. So completely different information than what you would get in your traditional modeling mechanism, but something that's very critical for you to be able to make your decisions, such as hardware, software, processing, or also decisions such as selecting your hardware components, selecting how I want to do the implementation. So what is the new approach deployed? First and foremost, rather than waiting for 18 months or 24 months after your signal processing algorithms have been done, you're gaining visibility right up front to what is my system going to be doing. What's going to happen from antenna to the Ethernet interface without worrying about all the underlying algorithmic details. So you have complete visibility into what's the constraint for each block. Now, should this function be implemented in hardware? Should it be implemented in software? If it is software, how many cycles can I accommodate? What's the data sizes that I can handle in each of these blocks based on the available buffers? And of course, the big thing, you get a demonstrator even before you started doing development. You can demonstrate that to your customers, to management, to any other set of people that might benefit from trying to understand what your exact system is doing. The other major use of these kind of approach, or this approach, is to provide better information for your proposals and your bidding process, because right here you know exactly what it's going to cost, because I know exactly what the hardware is needed to deploy this. So I'll have a better understanding to be able to make those decisions. Now, before I go off to system modeling, I want to make sure that you are fully aware of the chat window on the right-hand side. So I would recommend, if you have any questions, to ask them right away and not wait till the end of the presentation, so we can answer those for you immediately as soon as we get access to it. Now, when we get to system modeling, there are really two flows available in system modeling. The first flow in system modeling is about the data flow. It's about data coming in on an ingress port and departing on an egress port, and there's a sequence of operations. Can be scheduling, packet management, data storing, stripping off, encryption, decryption, modulation, demodulation, any of those kind of combination of things. There, what we're interested in is what is the sequence of activity that's happening, what is the buffering, what is the delay. That's really what we're looking at. Now, the next level is the algorithmic mapping. There, we know that this is the specific sequence of these algorithms. How best do I map it? Do I put everything on, as I was saying earlier, a Xeon processor, or say I take one of these functions, like say maybe an FFT function, and say I'm not going to do it on the Xeon, I'm going to do it on an FPGA. So, so I can get an extra performance for that one because that's the one that consumes most of the Xeon processor processing. So there are two different approaches that you can take for system architecture. Now, when I look at it, the flow-based approach, what you really see is a lot of queues, a lot of delays. So there's queues, there's delays, a lot of muxes and demuxes. There's also concepts of intermediate activities. There's also feedback loops, lots of feedback loops. The other one is the scheduling. So you can have a rate limited, weighted round robins, the default round robins, strict priority, any of those kind of things that you can utilize in your in a system flow. Also notice there tend to be lots of channels, and so you get data on a huge number of channels, and you need to match them to the output. Plus, you need to handle the credit policies between the output and input. So a lot of communication across the system. Now, the VisualSim model looks identical. So you have your traffic for these. You have the queues as you saw. You saw the this is the controller, which is your scheduler that we had marked right over here, the scheduler. And of course, then you have your intermediate queues. Then these mux into a single queue, and then you have statistics and display plots. And of course, the main thing is you have the parameters, which you can vary. Variety of statistics, you get latencies, buffer occupancy, and of course, complete statistics for each one of the queues. So for example, you find that these queues mostly don't have any buffering, but you can see they all have variable amount of data coming in, and you can see what's the delay through those particular queues. So it gives me the visibility into what exactly is happening in my particular system. Now, going over to VisualSim. So this is the VisualSim modeling environment. As you can see, we've got the libraries on the left-hand side, and you can see the block diagrams, the blocks. So if I double-click on any of these blocks, you can see each one of them has a unique set of parameters. So for example, if I click on this one here, I can get a processor module. Whereas if I click on, say, resources, I can get a queuing module. Or if I click on, say, hardware devices, I get some of the peripheral devices and VMAs. Or I can click on these, I can get more of the the networking and the buses and things like that. So a variety of building blocks, and drag and drop them, and each one of them has a unique set of parameters. I can create those up. I'm going to go ahead and click on this. So you can see there's a variety of statistics. Every model, you can create a different set of statistics. It really depends on what is the type of analysis you want. So we have latency in an XY, but also latency in a histogram. You can see statistics written out this way, while you can also have statistics written out this way. So here, for example, I'm looking at every signal or packet that comes in, and I track from the ingress to the egress, what was the time at each point and what was the total latency through it. So that way I have full visibility into exactly what is happening in my system, even before I started putting in my algorithms. It could be a policy algorithm, or it could be a signal processing algorithm, or it could be an analog front end, any of those kind of things. So it gives me full visibility. For example, I can try out different experiments. So like, for example, the ingress size, I can make it into 25. That means there's 25 queues coming in as opposed to 15. And now I can see how the latency changes when I go to a lower. So notice here, earlier we were buffering to about 30 when I had 15 channels, but when I went to 25 channels, my buffering stopped to 14 because it's the same amount of data samples that's been split across more number of channels. So that way I can reduce the amount of traffic going on to each channel, so that way reduce the amount of buffering. So what do I know from here? I know how many ingress queues I need. That's one of the spec I need. I know what's the buffer occupancy in each one of them. I know what the flow control is between all of them. So I get all of this information into this, for this particular model, using this particular model. Now, going back to my presentation, We saw the the data flow version. Now let's look at the application or the block diagram versus mapping version. So what that means is I can define a hardware thing. So this looks more like your box or your chassis or your board has multiple computers, IOs, DSPs, bridges, and buses. And this forms the hardware resource, or what we call the resource hardware blocks. Then what I have is I've got the application. So here the application consists of three parts. The first is the variable rate input stream. It can be signals, packets, data, requests, any of those kind of things. I have concept of tasks, and then there are transfers between the tasks. So each task gets mapped to one of the resources in my system, and the transfers between them are these. So for example, when I take 2 to 3, 2 is going over here, 3 is going over here. You can see that I have to go bus 1, bridge, bus 2 to DSP. So that's my transfer information. Now, one of the things is today's systems typically are not just running one application. Also, they're not just running one core, they're running large number of cores. So what I have to do is, I'd have multiple applications, same way, tasks, transfers, and input streams. I can map all of them. So you can see I got 4 tasks here, 4 tasks for second application, total of 8. And I've got 6 transfers, 8 resource mapping and 6 transfer mapping. Now, what are we trying to do with this kind of a model? This kind of a model, what we're trying to do is we're trying to figure out how can I increase the processing time versus the transfer time. Processing time is the execution of the resources, or the transfer time is the time that goes on the buses, bridges, maybe IOs, interfaces of PCI Express, for example, going to memory accesses, things like that. So I'm spending more time doing the execution and less of the time going and getting data or moving data around. The other option is I also want to see how I can minimize the power consumption, be it in a satellite, aircraft, or in a data center. There's the operational cost or battery cost or even the the energy harvester cost that have to be reduced. So now when you look at the VisualSim model, you see a very similar environment to what you saw earlier for the block diagram. You still have your library folders. You can see the parameters. You can see all the reports. But now things get different. You don't just see one flow. You do see the flows here, which is really related to the application. So you see the workload generator, similar to that one, but you have multiple workload generators. And here you describe what your behavior is. There, I had the data flowing through a set of queues and delays, and I had feedback loops and things like that. But now, what I have is I've got these flows here where this one says gets mapped to the IO. For example, the CPU, it's getting mapped to CPU 1. And of course, there's transfers that go between them. The important thing now is that we have a separation of the behavior, which is all of these functions, and the architecture. What's the advantage? Now, from a radar standpoint, say I've got 2 different radar applications. I can change one of the flows here, okay? And I can say I want to do a different kind of a mapping. Or I can add another flow and add that to the system. I don't have to redesign my algorithms. I don't have to input all the map. It's simply just a process of mapping these functions. So huge acceleration of my analysis. So if we look at the statistics, so earlier on, if you looked at the last one, it gave me information about number of queues, how many channels I need, the buffer sizes, what's the data input rate. Here, what's changing is how many applications can this hardware platform support? Now, if I start making tweaks to the hardware platform where I say, let me try one Mercury box, for example, which is running 200 megahertz, versus another one that's running 400 megahertz. Which one's better? Really decision based on what you're looking for. In this case, the 200 megahertz, which is the red dots, is slightly higher than the 400 megahertz latency. But there are certain points over here, these circular ones, where the 400 megahertz bus actually increases the latency, which means there's a much higher latency for the implementation using the 400 megahertz. Now, in the normal circumstances, maybe it's not a problem, but there are other events that can cause it to be a problem. What are those? These could cause buffering of the future events. That could be one. These spikes could cause increased power consumption. That relates to thermal cooling. So you have that impact. And the third one is these might be beyond the timing deadlines, which means it's not acceptable range within which the system needs to be operating in terms of response time. So that's the kind of thing that you can analyze from this. Now moving over to VisualSim to look at the model, you see here, there's your libraries. And I said you can click on any one of them, drag and drop them. So for example, I can go in here, I can go in here, and I can drag and drop in, say, a processor block. Now here we have the two CPUs, DSP IOs, bus, bridge, bus. You can now see the software here, right here, where the traffic rates. So for example, here I can go in and bring in, say, a TI DSP, for example. And it's got its own set of attributes right over here. Or I can bring in a 10 silica block. So there's a whole bunch of these components that are available right in the system. Now, this one here, if I click on this, you see that this gets mapped to the CPU, which has a clock speed of 400 megahertz. And there's also a timing delay, which is right over here. Now, the transfers is a little more complex because I got bus 1, bridge, bus 2, and there's a number of cycles for each one of those. So the delay, the actual delay will not just be that 14 cycles, because the actual delay will include the queuing time. If you have preemption on your processors, your preemptive time, and of course, other things like read-write, memory accesses, and things like that. So delay is more than just that processing element that you saw there. Okay? So now I'm going to go ahead and rerun this simulation. You can see your power consumption. You can see the latency for application 2. Plus, you can also see the statistics. So for example, the DSP is 48%. But if I look at the IO, that's 81% utilized. So I really don't know if I can add any more workload. The bridge is not that much. The bus 2 is not. But when I get up to CPU 1, notice it's 92%. So now, if I say make this 300 megahertz, so from 400, I'm making it 300. So I'm trying to see if I can cut costs, reduce power, things like that. But notice I can't, because it says task dropped by system resource CPU 1. What's that telling me is that the number of transactions coming in is greater than the capacity of this particular hardware system. Now, here's what I can do. I can say, you know what? I'm going to reduce everything down. Let me reduce the bus speed down. Let me see what that does. Notice it doesn't even last. It's like the data is coming in so fast that the bus can't even handle it. Oops, sorry, I set that to be 242. Let me make it 200. It actually went a little longer. So here's where you can actually do different types of trade-off studies. So for example, here you can see this function here in this flow here is the software task which has my performance limitation. So this is one of the things you could consider is, rather than doing this on a generic processor, I could move this to a hardware accelerator. Then I could get better performance. Now, what I can do is I can go back to this to 400 megahertz. I can change this to 200 megahertz. So here I'm not changing the processor, but I'm changing the the bus usage. So you can see how the latencies go up, what was the processing versus transfer time. So this model allows me to figure out what should be the configuration of my hardware components, what should be the mapping of my applications onto the hardware resources, and also trying to identify if there's any candidate that needs to go into acceleration, that needs to go into a separate accelerator. Okay. Now, as I mentioned, if anybody has any questions, feel free to post it in the group, and there'll be someone here that will respond to you right away. Now, there are other statistics that VisualSim provides. I just thought I'd list some of them. So you can see there's throughput, there's latency, there's power consumption, buffer occupancy. There's a variety of other statistics that you can also generate. So this goes beyond or the standard statistics we were already discussing. Now that you understood why we need this new approach and understand the systems engineering methodology, now let's get to the next level, which is really understanding how systems engineering works. One of the key things in systems engineering is that it's a multidisciplinary or a multi-domain system. What that means is it's not just all electronics, not just all mechanical, not just all electromechanical. It's actually a combination of RF, hardware, software, thermal, power systems, mechanical. So it's a variety of the elements are included in that. Now, one of the key things in systems engineering is when you start off with the systems engineering process, you want to be able to reuse those test cases that you started off with originally down all the way to implementation. So you want to make sure that the test cases you create at the system level are robust and they're going to be able to identify the faults down to the implementation and to the deployment level. So planning on your test case is very important in the system engineering process. So now let's look at what are these test cases. So here we have an aircraft. So test cases are, what it moves or which order or which sequence it goes. And this is my model of the aircraft. And one of the things you can see here is I have data flow, which means, it's electronics and it's software. But then I also have power and thermal connectivity right here, which are these dotted lines here. And of course, there's a mechanical structure which kind of is given for a fixed system. And of course, you can see all these other ones. Eventually, when you want to go for implementation, you can put them in their respective environments or their respective tools. So you don't actually have to go back and forth with VisualSim providing half of it and the downstream implementation tool providing the other half. But rather, once you're done with this, you provide all the information to the implementation tools that'll go off and actually do the implementation. So now this is the model. You can see the trigger, which was these test cases. And you can see all the hardware, the software, the mechanical systems all provided in your block diagram. And of course, you can see over time, you can see what state each the aircraft was. And this were the test cases that we had deployed. And here, for example, you can see the RF power consumption. Well, this one here shows me, for example, what's my link margin, what's the power consumption. So it shows me a variety of information that I wouldn't otherwise be able to get, especially at this level of modeling. So now that we've seen this, we would move on to the next portion of our presentation, which is surrounding the hardware-software mapping of radars and signal processing applications. Now, again, I'm going to stop for a few seconds just so that anyone that might have any questions can go ahead and enter them, and we would answer them in the order of arrival. Okay, so if I take the radar architecture challenges, there's really three levels, which is the first one is the systems engineering. Systems engineering, I want to be able to take the power systems, the hardware and software, capture all the requirements, figure out what the link margin is for the RF, what was the thermal requirements, what's the response time on a potential hardware platform, what was the throughput, being able to capture that at a very abstract level. Enough to make a proposal, enough to create a detailed document, but not enough to do the implementation. That's where the hardware software selection comes into play. At this point, I'm really curious about, if I want to map this to an FPGA, what's going to be the data size coming in, what size goes out, what's going to be the expected delay. I'm going to do it on a processor. I'm going to worry about, how much data can I bring in at a time to do the processing. So it's like whether I want to do a batch versus a single selection. One of the key things that a system model allows you to do is eliminate deadlocks. So what that means is downstream, there's certain tasks that cannot start until a set of input tasks have reached them. So which means that the input tasks have have either been buffered, or they're waiting for data from another part of the application, or they've been targeted at a specific resource, and that resource is not available because the previous application requires some other data that is currently not available, things like that. So you can try your hardware software selection, and this takes you closer to implementation. The other piece of it is the system level. What we mean by system level is really taking the radar and deploying it in an application. So what are the types of applications? You can look at things like, autonomous driving, or a tracker on an aircraft, or other types of radar applications that give you the the ability to see how this particular hardware software combination works in the context of the final product, or the final resting place of these systems. Now, this one here is what we call a template model. So in VisualSim, we've got over 150 templates that we provide you based on the target application and based on the level of detail that you want. So in this case, we have the mapping of the radar application. So you have everything from the analog A to D all the way down through the FFTs to the IDFTs, and finally coming down to the static and moving target estimation, which is kind of an output at this stage to show you when there were any messages that came in that user needs to be worried about, or the controller person needs to be worried about, maybe engage an aircraft or things like that. Now, one of the things here you're going to see, you might consider this to be very similar to the flow diagram that we looked earlier with the sets of cues. It also looks very similar to the behavior model you saw in the hardware software mapping. So which one is it really? This case, it's really about the mapping. So what that means is I get data coming in on an ADC source. So it comes in on some sort of an analog interface. There's some initial buffers. And then you have the first function, which really is a cache that you're implementing on an FPGA. But the rest of the system gets implemented purely in software. So what we're trying to do here, is trying to figure out two things. One is, do I put this on a 12-core Xeon processor-based Mercury computer box, or build a fully custom DSP-based hardware architecture? So no right answer, depending on your power, depending on your processing capacity, depending on your latency, one might be better than the other. Just something to consider. Now, when you compare the mapping, you can compare it in many different ways. In this case, we're looking at two ways. One is, what was the activity over here? The second thing is, were all the cores busy? The hope is, if only a few of the cores are busy, then it means that I could reduce my cost. I don't need to buy a 12-core. I can buy an 8-core Xeon processor. Of course, the throughput is the most important thing. How many images am I able to track? That's the most important thing that we're interested in. So now, if I go into VisualSim and I look at that model, what you see over here now is you see your sequence of flows with some dependency over here. There's like two tasks running in parallel. But now let me take the a block in here. And what you see here is a mumbo jumbo of stuff, but reality does make a lot of sense. First and foremost is, which case selection do I do? So there is the case here. So if I click on this, I can see I go to 1, 2, or 3. So it's like 1, 2, or 3 down here. That's a parameter. So every time I can change the parameter and try something new. Now, when I go in here, I have another one, which is I'm based on whether I'm within the threshold or I'm greater than the threshold. So that's a major consideration. So depending on if I'm within the threshold, I'd go there. If not, I'd go down to this lower level. Other things, for example, here, the data size is 800 bytes, but I'm taking 400 bytes and processing them. Why is that? That way, I can pipeline my system better, so I need less amount of processing capacity, and faster memory accesses, things like that. Of course, you have the other flows having different data sizes and different requirements, but the top one is where we'll focus on, which shows me exactly, what was the processing requirements and what was the memory access, because I know that, this function coming in has all the details on the implementation in terms of how many cycles. So we take all the basic information, extract out the PRI, CPI information, and then we get the samples and we probe we set it up such that the two things. One is the size of data, and the other one is the cycle time. Why do we need two things? There are two reasons for it. The first one is the bytes is typically for buses, memories, networks, things like that. The cycle time is typically for the processor, maybe caches and some DRAMs as well, but primarily the processor. So here what we're doing is we're doing a computation to come up with that value of how much should be the bytes and how much should be the cycle time. Now I can go ahead and run the simulation. Notice here you can run these simulations dynamically from the GUI, or you can schedule it on the for running on the command line, and you can run like hundreds of those on a server farm and come back in the morning and just just visit the statistics. We have a block called a post-processor block that allows you to do that. So here, for example, what are we seeing? We're seeing the static flow, the moving target flow shows my my throughput. And of course, these are related to performances. You can see these values keep changing right over here. Now, it's possible for me to change the data sizes, possible for me to change the mapping. So, for example, if I decide that I need something a little bit more integrated, then what I might do is, rather than implementing it say on a Xeon processor, I might change the implementation. Say now I'm going to implement it on, say, a DSP from TI. So what this allows me to do is allows me to look at which implementation is better. So when I go back to the top level over here, what I see is different attributes for each block, but in reality, they're getting mapped to different resources. Now, if it's possible that you have in-house programming environments, or you have these external processing that can happen outside the company, and some of them can be built internally. This provides you the ability to specify who builds which component, either within the company, within the team, different team, or even within a different organization altogether. So you can provide that information right over here. They see that, and then they can go off and do the implementation. At this point, I'm going to take a short break and see if anybody has any questions, wants to ask anything. They can go ahead and do that. Now, one of the things that's critical in all these complex systems is the failure analysis. The reason it's critical is because of the fact that I want to be able to know, am I at the maximum robust situation I could ever be, or is there something worse than that? So now, to be able to understand worse than that, you still have to be alive, and you still have to be doing some sort of a research. So, for example, here, you can have a variety of failures: hardware, software, network, RTOS, and power failures. So depending on your design, you can select one or the other failure as well. And you can decide which one does make sense for you to do a further investigation, or everybody's saying, oh yeah, these are all within my boundaries, so I don't have to worry about them. Now, one of the key things with functional safety and failure analysis is that These are what are called continuous assessments. So with regards to continuous assessment, typically the information is stored in an Excel spreadsheet, which is exactly what we do in our model. So we store the list of failures, how we generated them, what was the outcome, and whether it's a fail or a pass. So that way people can look at this and know exactly what they need to do for their implementation. Also, it is a requirement for the signaling authority to be able to provide all of this in a spreadsheet format. Now, there's a concept called ARP 4761, which is different from the DO254 or the DO178B. It's really all encompassing. And what it says is that when you generate the models at the system level and also test at the system level, which is, think about it as a whole aircraft or whole car, in parallel, you want to also work on the requirements. The reason is, when you're ready, you're going to be allocating these system model tasks to different cores on the processor. So, which means that you're actually being able to see how I can better engage in terms of engage, meaning that I get a better throughput or I get a better response based on how I allocate the system functions. Now, the concept of the system concept of these failure analysis and functional safety testing is that one of the key things is iterating over hardware software partitioning. So once I made the decision on hardware software partitioning, you want to add test cases to ensure that your hardware software is really at a stage where it's going to be it's going to meet your timing, going to meet your throughput, going to meet your functional and behavior analysis. And of course, the other piece of it, which is the continuous systems engineering, which means that what I do in my implementation can be fed to the, what I do in my systems engineering can be fed to implementation and to the deployment guys, the guys that are going out into the field and deploying it. We want to be able to use the same test cases, the same test data at all these different levels. So that's one of the things that's very critical, that you want to start up front, being able to generate these test cases. As I mentioned earlier, anyone has any questions, feel free to use the chat window so we can answer them right away for you. So before I talk about Mirabilis, I just want to do a conclusion on the radar system itself. System modeling, where using VisualSim or using something at the higher level abstraction, is threefold. One is you can get real accurate values of power and latency. The other one is you can come up with a hardware configuration that's already been tested before you start working on the algorithm, before you start optimizing your FFT or your FIRs or your Taylor curves, things like that. You could do all your optimization of the hardware platform selected before you start the development on that one. One of the migrations today is multi-core and also multi-processors on a single board. So your application should be able to support it, especially if it already exists in the system you're getting. So that way you can maximize the number of images that you track, or the in the future looking at potential latency as well, which is minimization of the latencies. Now, this one here is a webinar and a hands-on workshop. So one of the things we provide you as part of the workshop is the right for you to download the software and use it. Now, as part of this presentation, I've included these that are built into VisualSim, so you can try to play and see how they operate. Quick introduction to Mirabilis design. Mirabilis design has been around for about 15 years now. We have a huge number of awards and fairly large customer base. We've got over 250 products designed. And the last thing is that we've been getting a lot of accolades at different conferences and shows, but now we're starting to do functional analysis. Functional analysis at the system level has never been attempted before. So this is kind of a new technology that we're introducing. We introduced portions of it, but we're going to have a full-fledged deployment later this year. What do we provide as Mirabilis Design? Two things. The first is the software, which is VisualSim software and the libraries that you saw there. And second one is custom development. Can be training, can be I just want to build some building blocks, build a whole model, and if required, even do the architecture analysis. So this is something that you may want to consider, is depending on what level you want to be at, meaning, how quickly you want to finish your project, how many resources I have, am I able to get resources in the future, not having all of those, you may consider services along with the tool purchase. Okay, let's talk a little bit about VisualSim Architect. The purpose is to really architect different hardware components and then map the algorithm onto that hardware component. The hardware itself can be a distributed hardware or it can be a fully integrated hardware. Why is there a difference? The difference is that, remember the transfer time. So if I have to go distributed, which means I have to go from this, the AFE part of the system to like the moving target part of the system, they go across. So there could be a huge lag across the PCIe bus, which means that my GPS input that's coming in later in the time may not be very accurate. We have those kind of challenges. The other thing is really you're looking at, I've got these task graphs for my software. What is the complete resource requirements? How much of resources do I need to effectively continue running up the system? Now, computing the resource requirements is very critical, especially if you have a very high-level software, a very high-level task graph description of your system. So, for example, if you look at that earlier model where, like this one here, you can see that's the sequence of application. But now some of these are in hardware. Actually, the first three is in hardware. Only then it starts getting more software. So you can see how I could maintain that information, also determine what's my the resource requirements. How many DSPs, how many accelerators, things that are required. The last one, and this is probably the most important thing, tests, the functional safety analysis, all of those that are done at the system level with VisualSim can also be progressively be fed to the lower and lower levels. So there might be levels where you want to just plug in the test cases and see the output and compare the results. Other cases, you may want to be where I only have this portion ready, so I put on an FPGA, connect VisualSim, and get the output out. So I can do those kind of things as well. Now, this one here is the comprehensive library that we provide in VisualSim. You can see anything from traffic generators on the left-hand side to processors and other virtual interfaces on the right-hand side. So as you can see, we have a huge library of components, and we add approximately 1 to 2 libraries every month. So if there's a new library that you're interested in, send an email and we can schedule it into our product development cycle. Now, one of the things in VisualSim is you saw was the library. So using the basic libraries, you can start plugging them in. The second one that we have are the templates, like you saw the radar template. Right? We have a software-defined radio template. We have the Power 10 template. We've got a template of the SSD system. So we've got templates of these different applications, and then we can see what the performance is going to be when we apply the faults. So the idea is that to see, does it recover after the fault occurs? So for example, say the RTOS has multiple slots, and say a task which is in slot 2 always overlaps to task 3. To slot 3. What do? The first thing we do is we shut down the slot and then try to restart it and see if the problem goes away. So that would be part of the model and part of the experience that you would note for your user, so that they can modify that part of the system. Now, as I mentioned, it's timing and power are the key things that we generate out of VisualSim. But feeding that would be things that, you're adding your risk components, which is, failure analysis, security, things like that. And now you want to look at, the capacity, the efficiency, the buffering, all of those kind of attributes. Now, why do people deploy VisualSim? There's two main reasons. The first is that the model construction time drops from about 6 months down to about 1 month. Why is that significant? Because now I can create a higher quality product, because a lot more of my time is spent doing analysis rather than going to the to a neighborhood and trying to go buy the chips, assemble it, and put a prototype together. Rather than doing that, I can do all the analysis, and also I can debug, because I can go and change this mapping here for this thing, or I can put in another AFE, an analog front end, or I can increase the antenna power, see what happens. So you ensure that you get the highest quality, and then you do all the refinements right up here. So even before you started your implementation, all your bugs, your analysis, everything is completed. So guess what? You're not going to have bugs when you're actually doing your development. It saves you a lot of time. And the second thing is, the average gain for a 24-month project can be up to about 30%, which means you have a huge revenue increase as well that you can demonstrate. With this, I would like to wrap up the presentation on hardware-software partitioning of radar systems. If you have any questions, feel free to ask them. Our technical team is standing by. Okay, we'll have some questions coming on. This is a very good question that is being asked. The question is whether the results obtained by simulation will be highly accurate even if you try to implement the same model in real-time communication. So there are two things. One is, when you start off with a more abstract model, like you saw the data flow model, there we only consider a little bit of delays. So we really care about that it sits in a queue, delays it for a while, goes to the next queue, and so on. Now, when you get to the algorithmic mapping, the functionality is a little bit different, meaning that every function there, I try to understand what is that function going to be doing, meaning that it's going to be reading some data at a certain rate. It's going to be breaking it down into these smaller things and processing each one of the functions, okay? And, processing each one of these data sizes with the specific function. So we know what the data size coming in, we know what the reads and writes to memories are, and we know approximately what is going to be the latency to do the processing on the whether it's the FPGA or whether it's the processor itself. So using that, you can get fairly good accuracy. Now, the accuracy is really a function of knowing what is the complete sequence, what's the dependencies between them, understanding all of those. That will help you right there increase the accuracy. Also remember, the accuracy is only as important as what information you need for the implementation. So rather than getting to 99.99%, you may find that at 95%, the accuracy is sufficient because I've captured all the information. I know these are the data sizes. I'm going to run the FFT. I'm going to be running these types of batch mode. I'm going to be integrating the IFFT into a parallel flow, which means I send the FFT to one core, IFT to another core. I've already got all the information related to that. So I can get the accuracy that I need for making those decisions. One of the things is that the recording of the session and the slides will be provided to you at the end of this webinar. So if anyone else has any questions, feel free to ask them. There are no more questions. Appreciate your time. Thank you for attending this hands-on workshop. Make sure to request for the latest version of VisualSim. You can download it and try some of the experiments. All the templates that I showed you today during the session are all available in VisualSim, and you can improve your awareness of how to use systems engineering for doing hardware-software partitioning. Thanks a lot for your time, and hope to see you starting to use VisualSim soon.